All right, well, welcome back. This is week 3. We're already a sixth of the way done with the quarter, if you can believe it. This 2 weeks flew by a lot faster than the previous 2 weeks. It's amazing how actually having something to do occupies your time when you're stuck at home. But anyway, I wanted to start by going over the quiz that we had last time. Hopefully you guys saw your scores and my comments regarding what happened on your quiz. I did put those in through Canvas. If you did not get them, go check out Canvas and you should be able to see it. But I do kind of want to go over it as a group so we can see where any issues came up. So please feel free to interrupt me at any time with a question, either verbally or through the chat, and I will get to it. But let me go ahead and switch to the screen, to the whiteboard here. All right, so let's start with problem number 1. So problem number 1 was just some conversions. We wanted to convert from degrees to radians and vice versa. And so for the first one, 1a, we had negative 24 degrees. So if we want to go to radians, we need to use that ratio that holds the conversion. In this case, we're going to want to multiply by pi over 180. So we always want to put where we're going on top. So we want pi's. So I asked you to go ahead and leave this as a reduced fraction of pi. So we can divide into 24 and 180. Both of those are divisible by 12. So if we divide them by 12, we get 2 for the 24. And then for the 180, we get 15. So this ends up being minus 2 pi over 15. And I would say that the biggest issue on this one is people forgot the minus sign, but it's super important. We need to have that because that tells us which direction we go, right? Remember, negative just means we're going in a clockwise direction as opposed to counterclockwise. So there was part A. So part B, now we're going to go radians, and we want to convert this to degrees. So we're going to take the 3 pi over 8. And again, we want to use this conversion factor, but this time we're going to put it as 180 degrees over pi. Because again, our target is degrees, so that goes on top. So the pi's are going to cancel. We can take 3 times 180 and divide it by 8, and we end up getting 67.5. And we got to make sure we put the degree symbol up here. Without the degree symbol, that's radians, and 67.5 radians is very, very different. So I just saw Juan ask, do we lose points when submitting the quiz or test late? I was having trouble submitting. This one I didn't take anything off, and everyone was pretty close to the 1 o'clock cutoff anyway. I think that's going to be sort of a case-by-case thing. I would really love it if everybody got it in on time so they could upload it through Canvas, because that speeds up the grading process for me. But I do understand that things sometimes come up. Right? So I didn't take any points off here. And I think it's going to be a how far off are you? You know, if it's a 1 o'clock turnoff time and you get it in at like 1:03, I'm not that big of a dick. I'm not going to take the points off. If it's a 1 o'clock turnoff time and you turn it in at 3, then there's going to be a different kind of decision to be made. All right, so for 1B, it was 67.5 degrees. You could leave it as a fraction or as a decimal. I didn't really care. All right, so then the second one, this was the one where we had a sector of a circle, and we were told that that circle had a radius of 6 meters, and we are going through an angle of 37 degrees. And so the question was, what is the area of that sector of circle? So if we go to the area formula, it's 1/2 per squared theta. And so we're going to go ahead and put in our r. So we're going to get 1/2 times 6 squared. But the angle, we can't put it in as 37 degrees. Because in this formula, it must be in radians. So we're going to have to convert that to radians. So I'll take that 37 and multiply it by pi over 180. That gives me the radian equivalent of 37 degrees. So that times the 6 squared times the 2 is going to go ahead and give me the area of this, which is 11.6 square meters. So a couple of things on this. In this kind of situation, you probably want the decimal. I know some of you left it as a fraction of pi. That's okay. It's just in terms of application, most people aren't going to want that. They're going to want it as a decimal. The other thing, and this is the science side of me, is that put units on these things. Because if you just tell me the area is 11.6, that doesn't really tell me how big it is, because there's a huge difference between 11.6 square meters and say 11.6 square feet, square miles, square kilometers. So get in the habit of putting units on applied problems. In a math class, I won't take points off. However, I'm just prepping you for when you're going to actually need it, which is going to be in every single science class. I'd be surprised if you have science teachers that don't take points off for missing units. All right, so there was number 2. So number 3, this is one where you had the triangle given. At least you have 2 sides given. And I asked you to give me the angle, or the trig function values for the given angle. So your picture looks something like this. So we had our theta up here, and we had these 2 sides of length, 8 and 7. So if we're going to find the 6 trig function values, we need to know the third side, because they're all ratios of sides. But we can get this from the Pythagorean theorem. If I call this guy A, I know that A squared plus 7 squared equals 8 squared. So that gives me that A squared is equal to 15. So A is the square root of 15. So now we can get the 6 trig functions. So the sine is opposite over adjacent, which is going to be 7/8. The cosine is adjacent over hypotenuse. Let's say opposite over adjacent for sine. Opposite over hypotenuse. Cosine's adjacent over hypotenuse, so that's going to be the square root of 15 over 8. Tangent is opposite over adjacent, so that's 7 over the square root of 15. And then the other 3, we know that those are just reciprocal, so cotangent is root 15 over 7. Secant is 8 over root 15, and cosecant is 8/7. So if you have 2 sides, find the third side using Pythagorean theorem, and then you're good to go. The one other thing, rationalize or don't rationalize, I don't care. You wrote it as 7 over root 15 or 7 root 15 over 15. I gave you the same points. All right, so there's number 3. So then number 4 was that applied problem. We're out on a sunny day, and we see the shadow of a flagpole, and we measure that shadow's length, and we want to figure out how tall that flagpole actually is. So you're told that the angle of elevation to the sun is 54 degrees. So here's the picture. Here's the flagpole. We've got a shadow. We measure that shadow to be 3 meters. So somewhere up here is the sun. And we know the angle of elevation to the sun is 54 degrees. So angle of elevation, think of what elevation means. Height, going up. So an angle of elevation is where we go up. So if we rotate up, that's an angle of elevation. If we were to go the other way, we're going to go down, that's an angle of depression. But this is an angle of elevation. So we know that the angle to the sun is 54 degrees, and we want to find the height of the flagpole. So we're just going to use a trig function. In this case, we're going to use tangent. So we've got the tangent of 54 degrees is going to equal h over 3. So h is equal to 3 times the tangent of 54, which ends up giving us something around 4.13 meters. And again, put a unit on there so we know how tall we're talking about. So it's a little bit over 4 meters tall. So we're talking about 13 feet or so. And there it is. So if you did this, you put into your calculator 3 tangent 54, and you got a different number, that's because you were in radian mode. So watch out for that. Make sure you're in the correct mode when we're doing trig functions. So anytime you put an angle into one of the 6 trig functions, you got to know what we're measuring in terms of, whether it's degrees or radians, and tell your calculator the appropriate number or mode. All right, so there was number 4. Anyway, so most people did pretty well on this quiz, no huge issues, but hopefully you were able to see through my comments what you need to work on, because we do have an exam coming up. In fact, that exam is on Wednesday. Our first exam is already here. We'll talk more about that later. All right, so any questions on the quiz? Okay, so hearing and seeing none. How about the homework? Any questions on the homework? How's that going, by the way? So dead silence is probably a good thing here, right? Oh, let's see. So Kiva, 7.3, numbers 4 and 10. All right, let me write these down. Anything else before I hop and share my screen? Okay, well then let's go take a look at this homework and see what we see. So I'm going to go ahead and share my screen here. Oh, okay, Kiva. So 5 and 10, not 4 and 10. Ugh, my computer is so slow this morning. There. All right, so here's number 5. And it says, without using a calculator, let's compute the sine and cosine of 135 degrees by using the reference angle. So reference angle, let's remind ourselves what that means here in a second, but it also says we want to know what quadrant the angle's in, and then we want to figure out sine and cosine of 135. So I'm going to write all this up on the board. We'll switch to the board here in just 1 second. But let me get the important information, what we're trying to answer. All right, so everybody ready? Obviously, your specific angle might be different, but it's going to be the same kind of process. So let me stop sharing my screen. We'll go to the whiteboard here. All right, so we want to find the sine and cosine of 135 degrees, but along the way they said use the reference angle and then figure out what quadrant we're in. So my suggestion is actually to start with the quadrant. Let's figure out where this is. Let's draw an angle of 135 degrees. So let's just sort of keep track of our total angle as we rotate. So if we start in the standard position, this is 0. We start rotating, we're going to get up to 45 degrees, which is the halfway to the quadrant. Then we're up to 90 degrees. If we were to go all the way over here to the negative x, that's 180. So 135 is somewhere between 180 and 90. And so the question is where? Well, if we just look at the difference between 90 and this angle, 135 minus 90 is 45. So we have to do 90 and another 45, which brings us halfway from the positive y to the negative x. So there's our angle. So let's answer the quadrant question. So which quadrant is it? Should be quick and easy. All right, I'm getting the couple people I can see on the screen are giving me the peace sign. A couple of you wrote in 2 in the chat. So this is quadrant number 2. We're in the second quadrant. All right, so then what's our reference angle? So remember what the reference angle is? That's the angle in the first quadrant that has the same values for our trig function with just potentially different plus or minus signs. So if we're in the second quadrant, in order to get the symmetry, we really want to look at how far are we off of the x-axis. So we find that by just figuring out how much further we have to go to get to 180. So that's a subtraction question. And I see that Diego just threw in the chat that that's 45 degrees. So the reference angle is for sure 45 degrees. Because if we're on the unit circle, and I look at these 2 points that are on the unit circle, their x's and y's are going to be the same in magnitude. They'll just be different signs. So the way that you can find the reference angle in the second quadrant is always to do pi minus theta or 180 minus theta, depending upon which way we're doing angles, whether it's radians or degrees. Because if we subtract it from pi or 180, it just tells us how far away we are from that axis. All right, so that means we know the sine and cosine of 135 degrees are going to be the same as the sine and cosine of 45 degrees, just with potentially some of them negative. So let's think about 45 degrees. What's the sine of 45 degrees? Anyone got that memorized yet? You can look at your chart. All right, so Kai just threw in pi over 2. Oh, pi over 4, changed his mind. So pi over 4 is the radian equivalent of this angle. But for the sine, and it is what Kiva just put in, and Benjamin as well, it's the square root of 2 over 2. So the sine of 45 degrees or the sine of pi over 4 is root 2 over 2. And the same thing is true about the cosine. 45 degrees is kind of cool because sine and cosine are the same. Okay, but we're not done because the only other thing we have to worry about now are these things positive or negative? So the way that we determine that is by remembering our little mnemonic device. Maybe you remember all students take calculus. That tells us what's positive in terms of the big 3. So in the first quadrant, all of them are positive. In the second quadrant, since it's all students, sine is positive. So the sine of 135 degrees is going to be a plus root 2 over 2. And the cosine is going to be a minus root 2 over 2. So this is how you can use the first quadrant angles to help you find the trig function values for the ones that are in the second, third, and fourth quadrant. Another way to recognize these are plus and minus is to go back to the definition, the unit circle definition for these things. And on the unit circle, the cosine is your x coordinate. And so we see that over here, whatever this point is, its x coordinate is going to be negative because we're to the left of the origin. That's why that thing is negative root 2 over 2. And then sine is the y coordinate. And again, this point is above the x-axis. So that means it's going to have a positive y. So it's going to have a positive sine. All right. So is this good for number 5? Any questions on this one before we go look at number 10? All right. So let's go look at number 10. Share my screen again. All right, so this one, this one says, we want to find an angle theta that's somewhere between 0 and 360 degrees that has the same sine as 20 degrees and the same cosine as 20 degrees. All right, so let me just write this information just so you've got it. Really the important thing for me to remember is that 20 degrees. So let's go to the board. All right, so we've got 20 degrees, and let's think about 20 degrees. That's going to be an angle that's somewhere over here. And on the unit circle is this point, and this point is 1 so that its coordinates are going to be cosine of 20 degrees, sine of 20 degrees. Let me back up for a second here. I just noticed that Era's just put, wouldn't the reference lengths be 1, 1, and square root of 2? So you can have a triangle with the 45 degrees that would have lengths 1, 1, and square root of 2. So that would be this picture. But this is not on the unit circle. If you think about the unit circle, remember that means that the radius of the circle is 1, and the radius of the circle is the same as the length of the hypotenuse. So this one's actually not on the unit circle. If we were on the unit circle with our 45 degrees, then the hypotenuse length would be 1. And if you scale this down, you divide by root 2, you get that these other sides have to be 1 over root 2, which is the same as root 2 over 2. All right, but good question. Good question. And that really illustrates the difference between the unit circle and right triangles. All right, so the first one is for an unknown radius. I don't think I understand what you mean by that question. Never mind. Okay. If you can think about a different way of telling me what you mean, I'll be happy to try to answer it. I just don't know what you mean quite right. Okay, so let's come back to this guy with the 20 degrees. So the point on the unit circle is going to be cosine of 20 degrees, sine of 20 degrees by definition. The x coordinate is the cosine of the angle, and the y coordinate is the sine of the angle. Okay, so let's think about the two things that we're trying to do. The first one is we're trying to find an angle where the sine of theta is equal to the sine of 20 degrees. And what we want is that this angle is somewhere between 0 and 360. Right? We're just looking at one rotation. And let's not go with the boring 20 degrees, because obviously if theta is 20 degrees, this is true. But there's another angle. There's another place where we get the same sine value. So the way to answer this question is to figure out another point on the unit circle that has the same y. Remember, sine is the y coordinate. So we've got a circle here, right? Let me actually draw the unit circle. I know it doesn't really look like a circle, but we'll call it good. More elliptical. All right, so here's our circle. So we want to find another point somewhere on the circle that has the same y. Well, y is our up and down. So we're really looking for this point right here. Because this point, I don't know what its x coordinate is necessarily, but its y coordinate is actually going to be the same sine of 20 degrees. So we're looking for the angle that passes through this point. So we're going to make use of the symmetry. And the symmetry here says that this also has to be 20 degrees. So the 20 degrees is our reference angle. And so the question is, what is that angle? All right, so what is that? What theta is going to give us the same sine as the sine of 20? So Kiva just put 140, change it to 160. We got some 140s, we got some 160s. All right, so again, remember what we're looking for. We need this theta, whatever that happens to be, plus 20 degrees has to end up being halfway around. So we know that theta plus 20 is going to equal 180. So if we subtract that off, we get 160 degrees. So it turns out that the sine of 160 degrees is the same as the sine of 20 degrees. They are identical. So there's the first part of the question. The first part asks us to figure out what angle gives us the same sine. Now there are a bunch of other angles that do this as well, because we could do more rotations, we can go backwards, but we were specifically told to look for things between 0 and 360. Excuse me. All right, so now let's look at the cosine. So now we're looking for a different angle. I'm still going to call it theta though. And this time we want to find the angle whose cosine is the same as cosine of 20 degrees. So in terms of the unit circle, now since cosine is an x coordinate, we're looking for another point on the unit circle whose x coordinate is the same as the one in our reference angle. Well, x is our left-right, so we want to still be the same distance to the right. So we just kind of follow down here. We're looking at this point. So the angle we want now is that. We want it to be between 0 and 60, so it has to be in, or 0 and 360. So it has to be on our first loop. And so the question is, what is that one? Well, let's use the symmetry again. We know that there's going to be a 20-degree rotation to get down to this point. And so we can do a similar argument to what we just did for the sine. But for the cosine, we know that this theta plus that 20 degrees has to be a full rotation. So I'm going to write here that theta plus 20 degrees has to equal 360 degrees. So if we subtract off that 20, we get 340 degrees. So if you take the cosine of 340 degrees and get a number for that, you'll see you get the same thing as the cosine of 20 degrees. So this is how we use reference angles. We basically just figure out how far are we off of pi or 2 pi to figure out the angle in the respective quadrants. So notice that in the second quadrant, it was pi minus theta, or 180 minus theta. In this quadrant, in the fourth quadrant, it was 2 pi minus theta, or 2 pi, or 360 degrees minus theta. In the third quadrant, we're off by pi, but we have to add. So like if we're down here, notice this 20 degrees, we'd see that our theta is actually equal to 180 plus 20. So in this case, we have to do pi plus theta. Right? So pi plus our reference angle gets us that. So you're either going to subtract or add to pi or 2 pi, depending upon which quadrant you're in. I don't suggest memorizing formulas here. I suggest just thinking about the picture, because I think it makes a lot of sense. Why is this one pi plus that reference angle? Well, pi brings me halfway, and then I have to go a little bit more. Right? Why was this one pi minus? Well, pi brings us too far, so we got to back up. We have to subtract. Same thing over here. Why was it 2 pi minus? Well, 2 pi is a full circle, but we overshot, so we got to come back. So that's how I think about it. But I'm a real visual guy. I don't actually like memorizing. I don't like memorizing formulas, so I don't. I do whatever I can. All right, so is this okay for 10? Any questions on this one? You're welcome, Kiva. All right, well, we're going to continue playing around with the trig functions today. And specifically, we're going to look at sine and cosine. And we're going to look at sine and cosine as functions and what that actually means. So what I want to do first is go back and look at sine and cosine in terms of the points on the unit circle. So I'm going to share my screen again, and I'm going to bring up something that I showed you before, which was that Trig Tour thing that we saw from the University of Colorado. So hopefully everybody can see it, and you remember this from before. So this is a picture of the unit circle. I've got it set right now for special angles. So if we move, you can see that this is the first special angle. It's pi over 6. It gives us the x and y coordinates on the unit circle. And right now it's telling us cosine. The cosine is √3/2. But if we march around, you see that the cosine value changes to the various bits, various values that I had before, and so on. Okay, so you kind of remember seeing this, and if I'm not on special angles, I can just drag this and go wherever I want, so I can get all kinds of weird radians, but you'll notice that I still get a point on the unit circle, which are giving me my cosine and my sine. So when you look at your trig chart that we built, and we started seeing all those patterns about the repeated numbers and those some plus and some minus, that's going on here as well. Notice that we started with, in this first quadrant, the x values are positive, so our cosine is positive. Once we got past the y-axis, now our x values are negative, so cosine turned negative. So we saw it was negative in quadrant 2. It's still negative in quadrant 3. Once we get to quadrant 4, though, it turns positive. Right? So we are positive in quadrants 1 and 4, and so on. So we can see the same kind of patterns with tangent and sine if we were to go to those specifically.
All right, so let's play around with cosine. And in particular, what I want to do is I want to draw a graph. I actually want to draw a graph of cosine. So I'm going to go to another website, and this is called Desmos, desmos.com. This is my go-to site for graphing. I love Desmos. It's a great online calculator and grapher. You can do all kinds of things. And I've got all kinds of stuff set up here right now. Don't worry about this. I'll explain what they are in a second. But what I want to do is I actually want to plot points. I want to plug in angles and get out the values of cosine for those angles. So you'll notice that I have a bunch of ordered pairs here. So like this one, 0, 1. The way to think about this is 0 is our angle, and 1 is the cosine of 0. Pi over 6 is an angle. Root 3 over 2, that's the cosine of pi over 6. And so on. So this graph is a little bit different. Now, don't think of them as x's and y's. Because if we think about them as x's and y's and the unit circle definition, it's going to completely mess us up. Instead, think of this horizontal axis as thetas. So this horizontal axis is a theta axis. It's not an x-axis. It's a theta axis. And the y-axis, it's not a y-axis. It's the cosine values. It's those numbers that we got that were the cosine values as we went around the unit circle. Okay, so it's thetas are horizontal and the cosine values, the trig values, are vertical. So what I've got in this first set here are the angles from the first quadrant. So this is the top of your chart. If you go back and you look at your chart, these are the top 5, and the numbers here, like the 0, 1/2, root 2 over 2, root 3 over 2, those are just the values in the cosine column. So I'm going to turn this on so that we can see these points. So now you can see those points here in red. And so this is what we're getting. This point right here, the cosine of 0 was equal to 1. A little bit further over at pi over 6, the cosine value is root 3 over 2. When we get to pi over 4, its cosine value is root 2 over 2. And then the cosine value of pi over 3 was 1/2, and at pi over 2 we get 0. So there are just a whole bunch of dots that we get when we plot the points, thinking of them as we do with functions, input-output pair. We're plugging in an angle, that's this axis, and we're getting out a cosine value. All right, just so you can see how this works, if I click on label, it'll give me the values of these things. I'm going to remove this because it's going to get really cluttered if I keep that. But for example, look at this one. Pi over 6 is 0.866. That's what the square root of 3 over 2 is, at least the decimal approximation. And the same thing for pi over 4, 0.707. That's the decimal approximation for root 2 over 2. Okay, let me just turn those off for a second. So that's what we get when we plot the points from 0 to pi over 2, angles 0 to pi over 2. So this is the first quadrant. So angles between 0 and pi over 2 are the first quadrant. All right, now if you look at this next one, I haven't turned this one on yet. If you look at this next one, now you'll notice that these angles are bigger than pi over 2. This is actually a continuation of our chart. If we keep going down our chart after pi over 2, the next thing we get is 2 pi over 3. Then 3 pi over 4, then 5 pi over 6, and so on. And these are the corresponding cosine values. So you notice that they are the same numbers. 1/2, root 2 over 2, root 3 over 2. They're just negative, which means on the graph, when we come over here to the graph, what we should expect to see are similar dots, but they're going to be negative, which means they need to be down here below the x-axis. But they're going to be the same distance away. There's going to be one that's a half, so we'll get a negative a half. There's going to be the one that, this one was 0.707, so we should get one that's like negative 0.707, and so on. But this list, just so you can see, let me arrow over. So we got to pi. I continued. I went to 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2. Okay, so I went through all of those because those were all the ones that were negative. So let me go ahead and turn those on. So they're now a different color, but same idea. So notice that we're getting like the same shape. It's just upside down. It's now negative. So these are the different negative values till we get to 3 pi over 2. And then finally, this third one I'll turn on in a second. You notice this picks up after 3 pi over 2. We get to 5 pi over 3, 7 pi over 4, 11 pi over 6, and then finally 2 pi. But I went ahead and included those points as well, so this should turn on in green. And so what we now have is a graph of all of the dots for all of those special angles, right? So they started positive in the first quadrant, then they turned negative in the second and third quadrants, and then they went positive again in the fourth quadrant. Now, this is something I definitely want to point out. When I look at a graph like this, I will talk about the quadrants, and the quadrants are a little bit different because what I'm talking about when I talk about quadrants are the angles. So first quadrant angles are between 0 and pi over 2. So the first quadrant is just a little region right here along the x-axis. This is the first quadrant because these are first quadrant angles. The second quadrant is between pi over 2 and pi. So this strip, this is the second quadrant. So these angles down here, these 3 dots, these first 3 blue dots, those are actually second quadrant angles. So these are in the second quadrant. Hopefully you can see why this is a little bit confusing at first, because you might go, that's not second quadrant, that's in the fourth quadrant, right? This is the fourth quadrant. But this is the fourth quadrant of a different graph. If I'm looking at the unit circle, these are actually second quadrant angles. So then third quadrant angles are these next set from pi to 3 pi over 2. And the fourth quadrant is from 3 pi over 2 to 2 pi. So you really want to think about this. If you kind of look at my picture down in the corner, you want to think about this as strips. Strips are quadrants. So we're going from first quadrant to second quadrant to third quadrant to fourth quadrant and so on as we march along. Okay. All right, well, there's all those points. So basically we're doing good old, first time you ever drew graphs of anything, we plot the dots, put the dots in there, and we connect them. Okay, well, this isn't quite a complete graph. Even if we wanted to get more dots, we could continue because once we get past 2 pi, we're going to get the exact same values because now we're coterminal to those in the first quadrant. So we would see these red dots appear again to the right of the green dots. And then once we get to 5 pi over 2, we're going to see the pattern that hit down here where it goes down. We could also go negative. If we went negative direction, now we're going to rotate clockwise. We would similarly start seeing the same pattern. So let me turn on the graph of cosine. So this is a graph of cosine of theta. I know that on my graph on Desmos it says y equals cosine of x. Now think of it, it's f of theta is cosine of theta. It's a function of theta. And it looks something like this. It's a wave. All right, it's just a wave. And it keeps bouncing back and forth between +1 and -1, +1 and -1. Just keeps alternating back and forth. And it keeps repeating. We keep seeing the same thing over and over and over and over and over. All right, so there's a graph of y equals cosine of x. All right, well, if I go back, oops, not what I wanted to do. That's what I want to do. Okay, if we go back to Trig Tour, I just want to show you that they also have a graph of cosine of theta versus theta. I just turned it off because I didn't want you to see it yet. But notice that this picture is exactly the same as what we just drew. And again, this axis is theta. It's the angles. And this axis is the cosine value. But you can see, now if I go back to my picture and I just start playing around, what you'll see is as I rotate to a different angle, it's moving me along this axis because I'm increasing my angle. And the height of this arrow is actually the same as the length of this arrow, this horizontal arrow, which is my x-coordinate, which is my cosine. And so as I move around, we start moving into different pieces, right? So here's my first cycle all the way around, and I get back to this maximum, get to this top point. But if I keep going, now I'm on my second rotation, you notice that I'm getting exactly the same values because I'm coterminal to something in that first rotation. And okay, well, if I go and I complete my second rotation, now I'm back at the top again on my graph, and I'm ready to start going down. And then similarly, if I go backwards, so here's 0, if I start going in a negative direction, you notice that I'm still getting this graph. I'm just going backwards until I do one full loop backwards, and I'm back at the top. All right, so there's a graph of cosine. Now, I want to go back to the board, and I want to give you some terminology here, some things that, some words that we use to describe what we're seeing going on here.
All right, so back to the board. All right, so here are my axes. Again, remember this is theta. And what we saw on the graph of this was something that looked like that, and I just kept repeating. Okay, so this is f of theta equals cosine of theta. So I'm writing f of theta because this is a function. We plug in an angle, we get out a number. It's uniquely defined, so it is a function. So this is the graph of f of theta equals cosine of theta. All right, so first, let's talk about domain and range. So hopefully you remember the domain of a function. The domain of the function are the values that we can plug in. I know that it's also a tendency of us to call the domain the x's. I'm not going to call it x's here. I like to think of domain as the stuff we're putting in. And what we're putting in here are angles. Okay, so the domain of this is going to be the set of angles that we can actually put into the function. So the question is there ever going to be an angle whose cosine we don't know? Which really means, is there ever going to be an angle where we don't intersect the unit circle? And the answer to that is no. No matter what, we're always going to intersect the unit circle with the terminal side of the angle. And so the domain of cosine is actually everything. So we're going to write minus infinity to infinity. So you've seen lots of functions like this in your life where you can plug any number in. This is yet another example. All right, so the domain of cosine is all real numbers. That's actually a great thing because we can plug anything we want in. We know cosine's always going to be defined. It's one of the nicer trig functions. Okay, so now what about range? So range were the numbers that came out, right? When we think of domain and range, domain is what we plug in, range is what comes out. So for cosine, what's the range going to be? What numbers are we getting out? Anyone want to throw one onto the chat window. Okay, so Mariola just put -1 to 1. And I'm guessing you meant those to be brackets, not parentheses, since they're curvy. Yeah. Okay, so what do you guys think? -1 to 1? If you go and you look at your chart, what's the biggest value you see in that cosine column? Hopefully, if you're looking down that cosine column, the biggest thing you see is 1. Thanks, Will. All right, so you get a couple people saying it. So the biggest thing you see is 1, because all those other numbers, √3/2 was like 0.8 something, √2/2 is 0.7 something, a half, of course, is less than 1. So we see the biggest thing is 1. And we actually see that on the graph as well. On a graph, remember, range is the extension up and down, and there is a topmost point on this graph. We don't get any higher than this peak. Yes, that peak repeats, right? There are going to be lots of places where we get that peak value, but the largest value we're going to see is 1. And since we actually get 1, we want to use the bracket. So then similarly, if we look at the lowest point is going to be in one of these dips. We call it a trough. But if we're at one of these dips, that's as low as we're going to go. Yes, it gets repeated, but that lowest y value is actually -1. So even though we can plug in anything, we can only get out numbers between -1 and 1. All right, so for cosine, there's our domain and our range. Let's talk about some of the other things that we know about this graph in terms of just graphs, like intercepts. So let's write up here the y-intercept. Right? So the y-intercept, where we actually cross the y-axis, the vertical axis, it was this point right here. And we see that that's the point 0, 1. So cosine goes through the point 0, 1. And then if we look at x-intercepts, you'll notice that there are a bunch. There are an absolute ton of these. The first one we run into, this guy right here, the coordinates of that is pi/2, 0. Right, the cosine of pi/2 is equal to 0. So that's the first one we see. The next one we see is 3pi/2, 0. You see that on your chart, but that's another place where the cosine is 0. If I went backwards, so I go negative, this first one is going to be -pi/2, 0. You may remember that we saw that cosine is an even function, which means we get the same thing if we go negative as we got when we got positive. So that's going to be -pi/2, 0. This second negative one is going to be -3pi/2, 0. But they just continue. There's going to be another one and another one and another one and forever. But there's a pattern to it. What's the difference between pi/2 and 3pi/2? How much do you have to add to pi/2 to get 3pi/2? Think of that as a subtraction problem. If you take pi/2 and you subtract it from 3pi/2, you get 2pi/2, which is pi. So it's a distance of pi to get to that next intercept. And notice that that's always the case. From -pi/2 to pi/2, it's pi. add pi, and so on. So the x-intercepts, they're always off from each other by pi. So instead of writing out a huge list, because it's an infinite list and I don't have that kind of time, here's how we're going to write x-intercepts. So x-intercepts, I'm going to write pi over 2 plus pi n. And this is a total mathematician laziness trick. So what I'm saying, if you want to find an x-intercept, you take pi over 2 and add to it your favorite multiple of pi. So we reserve n to mean the counting numbers. So think about the counting numbers 0, 1, 2, 3, 4, 5, and so on. Right? We call them the integers. So we allow them to be positive or negative. But notice how this is going to give us everything. If n is 0, this is just pi over 2. That's this first guy. If n is equal to 1, pi over 2 plus pi is 3 pi over 2. If n is 2, pi over 2 plus 2 pi, that's 5 pi over 2, which is the next one. If I want the others, I let them be negative. If n is negative 1, pi over 2 minus pi is minus pi over 2. If n is negative 2, pi over 2 minus 2 pi is minus 3 pi over 2, and so on. So I'm going to do this a lot, especially with trig, where we're going to represent things this way, just to allow ourselves shorthand, so that we can include all the answers in a relatively quick and easy way. All right, so we've got domain, we got range, we got intercepts. Those are kind of the primary things that we do when we're looking at graphs of functions, or at least up to this point. But there's another special thing here that's special about this graph that you've probably not seen before up to this point. And it's the fact that this graph repeats. So when you have a graph that repeats, we call it periodic. So cosine is what we call a periodic function. Okay, so all that means again is that the graph repeats. And when you have a periodic function, often what we're interested in is what is the shortest distance. So in this case with thetas, but what's the shortest distance, shortest interval of things that we plug in that we can have so that we catch the entirety of the graph by just copying it. So for example, if I just went 0 to pi over 2 and I had this picture, right, this part of the graph, if I just repeated that, I would not get a graph of cosine, because what I would see is this like half a hump and then just another half hump, another half hump, another half hump, doing the same thing. So our period is more than pi over 2. So let's stretch it. Let's say we go from the maximum to the minimum. So I get both positives and negatives. So let's go a length of pi. Well, if I copied that, it still wouldn't be a graph of cosine, because what I would see is something that looks like this, right, where I keep copying that same bit. So we just have to keep adding more until we start getting enough that we get the repetition. And it's probably not that hard to see that once we reach over here to this other maximum, if I copy that, put it on, attach it in each direction, I get exactly the same picture. So the question is, how far do we have to go from 0 to get to the next peak? Well, if you look at your chart, you can actually see this, because at the top, we had at 0, we got a cosine of 1. And we finally run into cosine equaling 1 again at the very bottom, which was 2 pi. So for this function, what we've got is that the period equals 2 pi. So period is how far you have to go, the minimum length you can go before you start repeating your graph. Now, periodic functions are awesome because it means there's less you actually have to know about it. If I know what happens with cosine between 0 and 2 pi, I know what happens with cosine forever. Something that's not periodic, you can't do that. You don't know what happens forever with any little chunk. So you're going to learn that periodic functions are actually a good thing because it minimizes what we have to actually know. All right, so there's a graph of cosine. That's what this thing looks like. It just bounces between plus and minus 1. And it repeats every 2 pi. All right, so any questions on the graph of this before we look at something else? All right, well then let's do this. Let's go take a look at sine.
So I'm going to go share my screen again. And we'll go back to the Trig Tour. But this time, let's look at sine. Now, let me turn off the graph so we don't spoil the surprise just yet. But let me put on sine. And just want to remind you that when we're looking at sine, sine is the y coordinate. So you notice now we have a green arrow that points up because that's our y value. So sine is the y coordinate as we go around. So it starts at 0. And as we start moving, it gets bigger. Notice our y value keeps getting larger until we reach pi over 2. We get a y value of 1. And then it starts getting smaller again. Comes down to 0, then turns negative, and so on. But now it's the y coordinate on the unit circle. Well, let me turn on the graph of sine. And again, notice that as I move around, I'm getting the same length vertical arrow as the vertical arrow on the unit circle. But there's my graph of sine. So if you look at sine, sine is very similar to cosine. In fact, it's exactly the same shape. What do you notice is the difference between them? Anyone want to try to describe what they see as a difference between sine and cosine's graphs? Okay, so you see a couple people putting 0, 0 origin. Yeah, sine goes through the origin. You remember where cosine went through? Cosine went through 0, 1, but sine now goes through the origin. But other than that, it still does this repeat of, you know, from a peak to a trough to another peak to another trough and so on. Okay, so let me go back to Desmos and share that real quick. So I'm going to turn off all the dots. So all we have here, this is the graph of cosine. Now I'm going to draw the graph of sine in a different color. It's orange. So there are the graphs of sine and cosine. They're virtually identical. The only difference is, like you guys were saying, if you look at the intercepts, the y-intercept, one of them goes through 0, 1, the other goes through 0, 0. So another way that we can describe this is that one of them has been shifted, right? So imagine the graph of sine, it's actually the graph of cosine if we were to shift it over. Or sine, if we shift it over, gives us cosine. So they're really the same graphs, they just have a horizontal shift. So I don't know if you remember how you deal with horizontal shifts from pre-calc, but I will actually show you why these graphs have to be shifted over. Okay, well, before we leave this graph, I want to just talk about some of the things we hit on with cosine, like domain and range and all that. So if you think about sine, its domain is also going to be all real numbers because it extends forever left and right. You can plug any angle in. You will always get a sine value because the terminal side of that angle will always intersect the unit circle. Its range is also -1 to 1. And that should make sense if the graph of sine is just cosine shifted left and right. The up and downness doesn't change. So cosine and sine have the exact same domain and range. But when we look at intercepts, they're a little bit different, right? We already saw the y-intercept is different. On sine, we go through the origin, where cosine went through 0, 1. But also notice that the theta intercepts, the angles we plug in to get 0, are different. They're 0, pi, 2 pi, minus pi, minus 2 pi. So they're different location, but they're still the same distance away. They're still pi away from each other. And then if we look at period, the period is the same thing. If we just look at the graph from 0 to 2 pi, and then we just copy that, we get exactly the same thing. So a lot of the features of sine are identical to those of cosine. The only thing we have to realize is that the intercepts have changed. Okay, so let me go back to the whiteboard.
So let's kind of make a list of what we're seeing here, the difference with sine and cosine. So we're going to have sine of theta and cosine of theta. So let's start with the list of things we had. So we had the domain, the range, we had the y-intercept, we have x-intercepts, and I'm going to put period because those are the different things that we've talked about so far. And so for cosine, we can go ahead and just make this list. The domain was all real numbers. The range was -1 to 1. The y-intercept was 0, 1. The x-intercepts were at pi over 2 plus n pi, comma 0. And its period was 2 pi. So we already had that. Now let's look at the same for sine. So from that graph, we saw its domain is still the same. Its range is the same. The y-intercept, though, changed. Now it goes through the origin. So 0, 0. So the x-intercepts changed. They were at 0, pi, 2 pi, 3 pi, and so on. So the way I'm going to write that lazily is just n pi. So that'll be 1 pi, 2 pi, 3 pi, 0 pi, -1 pi, -2 pi, and so on. But then the period itself was also 2 pi. So a lot of similarities, just very slight difference. So now I can actually tell you the name of the graph, because you know how we like to have names for these different shapes. Like, for example, the graph of x squared, we call that a parabola, stuff like that. Well, these are sinusoidal waves. So the graphs of these things are sinusoidal waves or sinusoidal curves sometimes. So just so you know how this plays out with the name, anytime you see the word oid, O-I-D, that means shape. Okay, so anything that's an oid is a shape. So this is sine-shaped. So we call them both sinusoidal waves because they both look like the graph of sine. So it's a sine wave. All right. So kind of cool that they look a lot alike. They're only shifted. So let me show you why. Let me show you why their graphs had to be shifted. So let me remind you a little bit about transformations first. and what it means when we have a horizontal shift, because it may have been a while since you've seen this. So let me just start here. If you want to shift a function horizontally, what you need to do is you need to add or subtract a number on the inside of the function. So for example, if we were to take f of x, but then instead put like x minus c, this shifts f of x c units to the left. Sorry, not left, right. Okay, so if you ever want to do a horizontal shift, we add or subtract inside the function. And what that number is tells us how far to go. And then in terms of right or left is just a difference of, is this a negative or a positive? And with horizontal shifts, it's always opposite of what you think. Okay. So I know that's a little bit weird, but it's always opposite of what you think. Okay, so that's how we do a horizontal shift. Now I want to show you why sine and cosine have to be shifted horizontally. I want to go back to the co-function identities. So for example, the cosine of theta, we saw that this was the same as the sine of pi over 2 minus theta. And similarly, sine of theta was equal to the cosine of pi over 2 minus theta. So hopefully you remember these. Just a fun fact about the co-functions and a right triangle. Since they're complementary, that's what this pi over 2 minus theta is doing. It's finding a complementary angle. So we know that these are true. Well, let's take the second one, just since it's on the bottom, and let's look at this as transformations. So this isn't quite right for our transformation because we need theta minus a number. So what I'm going to do is I'm going to change those around. So that this is cosine of negative theta plus pi over 2. Right, that's totally legit. It's just commutative property of addition. But now what I'm going to do is I'm going to factor out a negative. So the negative becomes positive, the positive becomes negative. So this is starting to look a lot more like what we should see for horizontal, because we now have our theta minus pi over 2. But I still have that minus sign in. Well, what's going to allow us to take care of that is the fact that cosine is even. Since cosine is even, that negative on the inside doesn't matter. So I can completely ignore it. I'm going to put here because cosine is even. So that's the step that lets me do this. Because cosine is even, the negative doesn't matter. So what we see, what this just showed us, is that the graph of sine is the same as the graph of cosine being shifted pi over 2 to the right. So I'm going to give you another second to write down those steps, and then we're going to go and look at the graphs again. And don't worry if you still haven't gotten all this, I'll come back to the whiteboard so you can grab that. But let me go ahead and show you the graphs again. But the key is cosine shifted pi over 2 to the right is the same as sine.
All right, so we're back to that graph. So again, this kind of bluish purple, that's the graph of cosine. The orange is the graph of sine. And notice that if you were to take cosine and shift it to the right, pi over 2, So that peak, now instead of being at 0, is at pi over 2. This minimum, instead of being at pi, it's at 3 pi over 2, and so on. But all of these points, if you move over pi over 2, you run onto the graph of sine. So the fact that we're seeing this, that these graphs are shifted by pi over 2, stems directly from the fact that these are co-function identities, right? That they are related to each other by complementary angles. So the good news here is that if you know the graph of one of them, you know the graph of the other. I'm a big fan of cosine. I will always show you examples with cosine. That'll be the one that I go to first, as opposed to sine. There are some reasons behind this. It doesn't really matter because you can do either one, but I like cosine, and so that's what I'm going to start with, mostly because we start on the top and it's easy to know where you go. If you're on top, the only way you can go is down, and then we can get going. All right, so there are how graph and cosine come about and how they're related. All right, so any questions at this point? Does it feel like it's a lot that you're going to have to remember? I hope not, because it's not really that bad. It's the same things we always are concerning ourselves with, things like domain and range and intercepts. Okay, well, let me go back to the board. And again, this will give you a chance, if you didn't catch everything, to write it.
So I'm going to leave kind of the bottom. We'll leave that for right now. But there's some more terminology I need to give you in terms of sinusoidal graphs. So let me draw a graph of cosine again. I'm not going to do too much of it. So remember that we just keep going if we want. So some other features about this graph that you should know. Like I mentioned, the tops, the words we use for these, you'll often see peak, like a mountain peak. So if you hear me talk about peaks of a sine wave, this is what I'm talking about. That's a peak. The bottom point, these are called troughs. So think about a trough like an animal trough where you feed them. So we have peaks and troughs. The math word for these are maxima and minima. So you have maximum values and minimum values. The plural is just maxima and minima, but I'll talk about peaks and troughs. But since these things are regularly repeating, and they're always the same distance to them up and down, we actually call that something as well. And so the distance from the center line, so in this case the axis, up to the max, similarly down to the trough. Those should be the same distance. On my graph, they don't quite look like it. This we call the amplitude. So the amplitude of the sine wave or cosine wave is just how far we go up or down from the midline. So then on the graph, you can see amplitude is a stretch up and down. Period, here's our period. So it's the distance from peak to peak. It's also the distance from, say, trough to trough. So this would be our period as well. It's basically the distance from any point to another point where it repeats, but it's easiest to see this with peaks and troughs. Now, we can easily change the amplitude and the period of a graph by doing transformations. So think about if I wanted the peaks and troughs to be further away. So I want to stretch that thing out. You guys remember how to do that with transformations? What do you do to a function to transform it so that you stretch it up and down? Okay, so William just put multiply. Yeah, it's a multiply. If you want a vertical stretch, and I'm going to put here stretch or compress because you can actually shrink them. You can squish them down. To do a vertical stretch or compress, what you do is you multiply your function by some c. And whatever that c is the factor of your stretch or compress. It's a stretch if c is greater than 1, and it's a compression if c is less than 1. And again, I'm assuming positive, because a negative flips it over. Okay, so if I want to change the amplitude, all I'd have to do is, instead of writing, say, f of theta equals cosine, I'm going to write f of theta is equal to a times cosine. And so that a is going to adjust the intercept. Instead of getting a maximum at 1, I'm now going to have a maximum of a. And notice that that distance, that y-coordinate, is actually the amplitude. So if I multiply cosine or sine by a number, I'm changing the amplitude. And that's why we usually use the letter a here, because this is going to be our amplitude. So we'll see some examples where we change that number and what it does to the graph. But that's going to change our amplitude. It's going to change how far we go up and down. All right, now, what if I want to change my period? So my period, that's how often we repeat horizontally. So if I wanted to lengthen or shorten that, I'd have to lengthen or compress horizontally. Well, the way that you do that is by multiplying, but we multiply inside the function. So for a horizontal stretch or compress, what we're going to do is have f of c times x. So notice that multiplying is happening in a different part. It's inside the function as opposed to outside. Inside changes things horizontally. Outside changes things vertically. All right, so it's a horizontal stretch compress. This one's backwards. The stretch happens when c is less than 1, and the compression happens when c is greater than 1. So in terms of our function, where we would see that is if I were to write cosine of b times x. And the way that this works in terms of the period is we're going to stretch or compress by that value b. But since it's opposite, it turns out that the period is equal to 2 pi divided by b. So in order to make it do the thing opposite, we have to divide by b. But b, again, is your stretching factor. And so it's going to stretch or compress. It's going to change that 2 pi by that amount, but we actually divide. But other than that, the shape is still going to be the same. We're still going to see it have peaks and troughs, and it's going to alternate. It's going to repeat. Just the repetition may be different, and the location of those peaks and troughs, how high they are, may be different. So we can actually put these together. And so in general, we're going to talk about what do the graphs of these things look like. So we're going to look at f of theta is equal to a cosine of b times theta. So if we just allow all those a's and b's to be whatever, we're going to be changing the graph. A is going to change our amplitude, and b is going to change our period. So what I want to do is go back to Desmos So I'm going to share my screen again. And we're going to just play around with A and B and see what happens when we change them.
Okay, so you should be able to see my graph again. So here's the y equals cosine and y equals sine. I'm going to turn off y equals sine. I don't want that to get in our way here. So we have just y equals cosine. Now what I'm going to do is I'm going to change this a little bit by putting vertical shifts, or sorry, vertical stretch compress and horizontal stretch compress in here. So let's start with, what if we go to y equals 1/2 times cosine of x. So think about what we're doing before I actually draw it. I'm changing the amplitude. Now I'm going to have amplitude of 1/2. So we've got a red graph now. That's the cosine of 1/2 x. But notice what happened. Now instead of going all the way up to 1, it only goes up to 1/2. And instead of reaching a minimum of -1, it only goes to -1/2. So we've changed the amplitude. It's half as tall as it was. And again, amplitude is from center line to the peak or to the trough. So that's got an amplitude of 1/2. Similarly, what if I drew one that's y equals 2 cosine of x? So now what we should see is our amplitude should become 2. We should go from the center line up 2 and down 2. And so now this is kind of our blue graph. And you see that as well. Right? Now we stretch all the way up to 2 and down to -2. But other than that, nothing else changed. The intercepts are still in the same location. The x-intercepts are in the same location. We still have the same period. It still repeats the same way. All we did was change the amplitude. So if you want a taller wave, multiply by a number bigger than 1. If you want a shorter wave, multiply by a number smaller than 1. Okay, so there's our amplitude. Amplitude changes are really easy to do. So let's do some period changes. And so what I'm going to do with this guy, y equals cosine, instead of cosine of x, let's make this cosine of 2x. So this is going to be a horizontal stretch compress. And so here's our graph now. So again, the purplish one, that's just regular cosine. And now this red one is cosine of 2x. So the way I like to think about it, again, if you kind of look at the picture of me in the screen there, I think of this as we just squished it. Think of a spring that we press together. Because now those peaks, like think about starting at 0, 1, we're at the same peak as we were before. But if we follow this graph, we get to the next peak faster than we would have when we were on the original graph, right? The original graph, we get to that first peak after we get all the way over here to 2 pi. On our other function, we actually get there in half the time. We got there in pi. So this now has a new period. If we know this graph from 0 to pi, that's enough for us to cut and paste and replicate the entire graph. So the period is now pi. So remember how I showed you on the formula for the period is 2 pi divided by the b. Well, if we take 2 pi and we divide it by 2, our period, well, 2 pi divided by 2 is pi. Let me change that to a bigger number, like 4. So now you see that it's repeating very quickly. The period now is going to be 2 pi over 4, which is pi over 2. And so you can see that we repeat from 0, we see our repetition at pi over 2. So when you multiply by a number bigger than 1, it's going to compress it. It's going to shrink it down so that it repeats faster. All right, well, alternatively, let me make that smaller. So now I made it y equals 1/2 of x. So that's our red line. And notice now it's been stretched out. It's going to take us longer to go from peak to peak or trough to trough. Now in my graph, I don't have another peak, so let's go look at the troughs. So this trough happens at -2 pi. The next trough happens at +2 pi. So that's a horizontal distance of 4 pi. So now our period is 4 pi. Well, again, take 2 pi and divide it by 1/2, you get 4 pi. All right, so that B is just changing your horizontal stretch compress, so that's changing our period. All right, now I'm actually going to stop with new stuff here. Don't run away just yet because I want to talk about the exam that's coming up. But next time what we're going to do is we'll just continue the story here and we'll look at what happens when we do shifts up and down and left and right and what they do to the graph. So let me stop the recording here. Oh, actually, before I do that, because I forgot last time to give you guys a secret word. Secret word of the day today, let me see what I got around me, will be water. Okay, so the word of today is water.